Dr. S. Venkateswarlu, working as a professor of ECE, IARE, Hyderabad. Yeah, today we're discussing about system classification in terms of the linear time invariant system and the properties of the linear time invariant system. Here, system classification, we know that the system is so we have that input and we will expect that output, that we require that the system. So, but normal system is different, but using the signal, what you call manipulation, signals, digital signal processing purpose, we require linear time invariant system with help of what you call discrete time system. User can verify that all signal variation and what you call effects of all goods. Here classification of the system. Here systems are classified into the following the categories. So the categories are depending upon their what you call direction or maybe shapes and so on. But here we are talking about linear and non-linear shapes. The time we require it is categorized what you call categorized that systems are classified into the following categories: linear and non-linear system. Time variant and time invariant systems, okay, of the static and dynamic systems. So of that causal and non-causal system, okay, of that invertible and non-invertible system, how it is affect with this system variation. So that we'll try to verify that what you call stable and unstable system. When compared to this linear non-linear system, and the last stable and system is very much useful for estimating your own desirabilities. Sometimes we require the time variant, sometimes we require the time invariant system. The system may be static or the system may be dynamic. We will expect that all static and dynamic system with what you call accuracy information. The time. Some systems are maybe causal or some systems may be a non-causal system. The time we require this causal non-causal systems. So sometimes we require that invertible and non-invertible systems for verifying this all either time domain and frequency domain variations is stable. Either maybe system may be particular accuracy or some error is affected or so on. The times based on this all analysis, supposed you have to verify this all character, what you call systems. Okay, so we'll see one by one. Yeah, here it is system based. Yeah, that system, we know that all system, that input may be x of t, or maybe we can say it is input is always maybe what you call x of t, or maybe x of n, or maybe x of t, or maybe f of t, and so on. So based on this all signal, this is the signal. The signal is input signal. With reference to input signal, it is fed to the system. System will respond. We will expect the system response is y of t. If the x of t is the input, we will expect that output response is y of t. Yeah, the system is, input signal is x of n. We will expect that output is y of t. Okay, so y of n. Okay, so like this, the system is, the system, so many systems are available here. With reference to this, all systems, how it is output response based on the input signal or the output signal. Whether it is how it is affected with this. So we will ready to verify after that our discrete time system, how it is reflected to the linear, non-linear system with reference to time variant and time invariant and static and dynamic, either causal or non-causal, or maybe the system is invertible or non-invertible. Maybe finally the system is stable or unstable system. We will decide. Within this, the system classification. So majorly, according to our DSP, digital signal processing, we require this linear time invariant system. So based on this linear time invariant system, so what are the major properties? So based on these all properties, directly we write to verify that what do you call our discrete time system. Variations and effects with this real time or what you call normal applications, how it is reflected mathematically and practically. That's why it's the major one is system is linear time invariant system. Okay, system is characterized by input, output, rules of operation. Yeah, the rules of operation may be basically varying the two modes, mathematical mode or practical mode, or maybe mathematical mode of the system. But here we should follow that rules of operation, mathematical model of the system. So based on the system input, or we can consider the or excitation, we'll expect the output or maybe responses. Okay, within this system, based on this all system, if it is using this all system, if you are using it linear time invariant system, what the effect or the output response? If the what do you call stable or unstable system out there reflected, or maybe if you are using the causal or anti-causal or non-causal system or the output response. So response is where right to observe the different responses. Okay, maybe you have to apply the rules of operation like mathematical mode of the system, how it is reflected with using these different systems. Okay, input is the signal. Based on the input signal, what is the response of the output signal using LTI system, stable or unstable, causal or non-causal, invertible or non-invertible system, how it is reflects. Okay, within this, the system representation. The system will represent with reference. The system takes a signal as an input, transforms it into another signal. So within this, in a very broad sense, a system can be represented as the ratio of the what you call output signal over the input signal, that way. So we can consider that system representation. So within this system representation, so when we multiply this system by the input signal, what happens? Or maybe we get the output signal. Maybe it's expected output signal, or maybe error, or maybe different unknown response. So okay, like this we will try to represent based on your different systems. Systems takes on the signal as an input and transforms it is another signal. Within in a very broad sense, a system can be represented as the ratio of the output signal or the input signal. That way, so when we multiply the system by the what you call input signal, so we will expect we get the output response, maybe output signal. Okay, so within this, using this all block diagram, system representation, block diagram or schematic diagram of this system representation. Input signal is x of t, that output signal is y of t. Okay, so within the input signal may be x of t or x of n, how it is reflected. Right to this x of n, x of t to system. The system is, we know a lot of systems are available. According to our view, around 6 systems are available. Based on using the different systems, we will expect that all output signal, maybe y of t or y of n or y dash of n, maybe response of your desirability, their desirability. Okay, so like this, we will try to expect that output response is y of t is equal to f of x comma x of t, because of using this all function y of t is equal to f of x of t. So coming to the one by one system, click on that all system, it will display the first system, the linear and non-linear system, how it is reflect, how it is affected with this mathematically and graphically, or affect with this different ways. So with this, the system is said to be a linear when it is satisfies what you call superposition and homogeneity or homogeneous principles. Okay, consider two systems with inputs as x1 of t and x2 of t. So like this, we would consider that x1 of t and x2 of t. Okay, so using this all output as we will expect this all output. This is the input using the different system. Using the system, we will expect the output is y1 of t. Because input is x2 of t, we using this all system. It is given to this x2 of t is given to this system. Okay, linear or non-linear system. Okay, we will expect this output response is what you call y2 of t. Okay, so the output as y1 of t, y2 of t. So then, according to the superposition and homogeneity principles, we will verify what you call this response of the overall system is equal to what you call response of the individual system. According to this superposition and homogeneity principles. Okay, so using this all, the response of the overall system is equal to response of the individual system. So like this mathematically we can represent t of a1 x1 of t is equal to a2 x2 of t is also equal to a1 into t of x1 of t plus a2 into t of x2 of t. So according to this superposition and the homogeneity principles, right, to verify that the response of the overall system is equal to response of the individual system. Okay, like this that so we have to verify that all t of a1 x1 of t plus a2 x2 of t is equal to a1 y1 of t plus a2 y2 of t. Like this, we try to use this all mathematical expression. We can decide that the response of the overall system is equal to the response of the individual system. Okay, next coming to this time or maybe shift invariant time invariance. So a system is time invariant. The system's output is the same. Okay, how it is same? So given this same input signal regardless of the time, so due to the offsetting the independent variable of the input by x naught, means this time or shift invariant time invariance. The system is time invariant if the system's output is the same, given the same input signal is regardless of the time. So within this, yeah, that the independent variable of the input by x naught causes the same offset in the independent variable of the output. So within this, as the input output relation remains the same. So it remains the same, but you should use the mathematical expressions. You can justify this what do you call this superposition, or what do you call a system is the invariant if the system output is the same given the same input signal regardless of the time. So with this, j of x is equal to h of fi of x implies that j of what do you call j of x plus x naught is equal to h of fi of x plus x naught for all fi of x, for all f of x, and for all x naught. Okay, like this you have to represent that mathematical expressions of that. So now coming to the static and dynamic system. Static, we know that our normal case is static and dynamic. The dynamic is all it is actuating. Static is somewhat it is sometimes it is the what you call constant. It will not be variable. It will not be movement. Movement is not variable. So normal cases. But according to our signal, digital signal processing, we have to estimate. We should manipulate the signals. The time we require that all. We need that static and dynamic systems. Based on that, we will try to calculate. We can measure this different parameters. Okay, that parameter may be static or dynamic parameter. The parameter in terms of this, by in this system, response of the given system may be static response or dynamic response. Okay, how? The static system is memoryless. Okay, static system is the memoryless. So whereas dynamic system is a memory system. We know that all memory and memoryless. We know that all importance of the memory and memoryless. If the memory system, we can store we can recollect this all or data. We can retrieve the data and so on. The memoryless, there is no storage. There is no retrieve the data or whatever it is. Say for example, y of t is equal to 2 into x of t. The present value is where f is where y of t is equal to 2 into x of t. Here in this case, where the present value where t is equal to 0, where t equal to 1, where t equal to 2, and so on. Where if we want to consider the t equal to 0, the system output is where here y of 0 is equal to what you call 2 into x of 0. Okay, like this. If you want to go on using this all, y of 1 is equal to 0 equal to 2 into x of 1 and so on. Y of 2 is equal to 2 into x of 2 and so on. Okay, so here y of t is equal to 2 into x of t. For present value is t equal to 0. The system output is y of 0 equal to 2 into x of 0. Okay, like this. Here the output is only dependent upon the present input. We have to consider this one where what do you call, if t is equal to 0, we have to concentrate this one 0. The time out is where is that y of 0. Here the output is only dependent upon the present input. Okay, that is your major observation while you are operating that present value. The present value equal to t equal to 0. Okay, remaining how they are using the solver we know, but according to this example, the static system is memoryless, whereas the dynamic system is the memory system. You can consider this where y of t is equal to 2 into x of t. For present value equal to t equal to 0. The system output is y of 0 equal to 2 into x of 0. The output is only dependent upon the present input. As the system is memoryless, or you can consider this what you call static system. Okay, by using this all the mathematical expression, using this a simple example, we can identify that system is static system, or we can consider that memoryless system. Okay, next coming to the next example where y of t is equal to 2 into x of t plus 3 into x of t minus 3. For present value is t equal to 0. How we are agreeing this all where y of t, here in this case y of where t is equal to 0, where y of 0 is equal to 2 into what do you call 2 into x of 0, isn't it, plus 3 into x of what do you call 0 minus 3. Like this, for present value is t equal to 0, so it is varies. So here for varying this all, what do you call, from this case, easily can try to verify that the system may be static or dynamic, or maybe memory or memoryless system. You can decide the factor. Okay, so here the system output is y of 0 equal to 2 into x of 0 plus 3 into minus 3, 3x and minus 3. Okay, so like this. So where here x of minus 3 is fast value for the present input for which, so what do you call the system the system requires, okay, the system requires memory. Why? Because of here that x of the once we are substituting this value, what do you call x of minus 3, where x of minus 3 is the past value for the what do you call present input. So which the system require memory, memory to get this output. Okay, this is the way. So hence the system is dynamic system. So like this you are able to justify that the system static system or memoryless or a dynamic system with reference to the simple example. Next system is coming to the next system, causal or casual and non-casual systems. Okay, so here a system is said to be casual or causal if its output depends upon the what you call present and past inputs and does not depend upon future input. That is nothing but what you call causal or casual system. So using this all simple definition, for non-causal system, the output depends upon the future inputs also. Okay, so like this example, y of n is equal to, here y of n is equal to 2 into x of t plus 3 into x of t here. So in this case, where y of here, if you are substituting that t equal to 1, that means y of 1 is equal to 2 into x of 1, where t is what do you call 1. We will substitute this. We can substitute this x of 1, okay, plus 3 into x of t is it is the same. Present value is t, where t equal to 1. So that means 1 minus 3. That means where y of 1 is equal to 2 into x of n plus what you call 3x minus 3. So like this. Okay, the system output is y1 of n is equal to what you call, so where y1 of 1 is equal to 2 into 1 plus 3x minus 2. Okay, so like this we can decide the factor. So we are deciding the factor, hence the system output is y of 1 where t equal to 1 it is substituted. So here the system output only depends upon the what you call present and fast input. Okay, that means the system output only depends upon present and fast what you call inputs. Okay, now here, so you can decide the thing, hence the system is causal system or casual system. So here for non-causal system, like where f of x is equal to 0 for x less than x0, implies that g of x equal to h of f of x equal to 0 for x less than x0. Okay, next coming to this invertible and non-invertible systems. A system is said to be invertible if the input of the system appears at the output. Okay, so here that x of t is the input, h1 of t, it is given that is 2 of t, what you call invertible system. We will expect that all y of t is equal to x of t. Okay, so here y of s is equal to x of s, h1 of s and s2 of s, since where x2 of s is equal to 1 by what you call that S2 of S is equal to, okay, 1 by H1 of S. Okay. So where here it is where y of S is equal to x of S, y of t is equal to x of t, hence the system is what you call invertible. So if y of t, if we are using this next condition, hence y of t, where y of t not equal to what you call x of t, then the system is non-invertible. Where y of t is equal to, so where y of t is equal to x1 of t, or where y of t not equal to x of t, you can decide the factor. If y of t not equal to x of t, then the system is said to be non-invertible system. Okay. So here, a stable and unstable system. The system is said to be stable only when the output is bounded for bounded input. Okay. For a bounded input, if the output is unbounded, the system is, then it is said to be unstable. Okay. Like this, where mod f of x, okay, less than k implies that where g of x less than c into k. Okay, like this, where say for example y of t is equal to x2 of t. Consider that where y of t is equal to x2 of t. So based on this example, you can decide the factor. So let the input is u of t, like unit step bounded input. So then the output y of t is equal to ut of t is equal to u of t. It is a bounded output. So now hence the system is stable. Okay. So using this all stable or unstable system, the system is said to be stable only when the output is bounded for bounded input. For a bounded input, if the output is unbounded, the system, then it is said to be unstable. So user can verify the stable or unstable system. So we will verify that some example like invertible or non-invertible system. So based on this, find whether the given system are invertible or non-invertible. So how we are finding? So here this given y of t is equal to phi of x of t. So where y of t is equal to 3 plus x of t. We are given two conditions. Third one is y of t is equal to 5x square of t. So use this all, verify this solution where the given system is, so y of t is equal to phi of x. So that means the system is available, y of t, the y of t where y of t is equal to 5x of t. Consider the same system. The given system is where y of t is equal to 5x of t. So with this, so if let x of t is equal to 3, okay, where x of t is equal to 3, then the output response, output of the system is, I need to verify. So based on y of t is equal to, so here the directly it is substituted where y of t is equal to, or what do you call this, y of t is equal to 5 into what do you call x of t is given. What is that x of t value? Where x of t is given, that is 3. So 5 into 3. So here y of t is equal to 15. Like this, we will ratify that what you call the first notation. Next, second one is where x of t is equal to 3, where x of 3 equal to minus 3. and the output of the system is, so out there verifying that output system is y of t is equal to, here same thing here, where y of t is equal to, what do you call, 5x of t. For this case, what do you call, where y of t is equal, x of t is given. That means where y of t, where y of t is equal to 5 into x of t, where x of t, where the x of t is given -3. So that means, so what happens here, y of t, so -3, 5 into -3 is equal to, what do you call, -50. Like this, right, to verify. Hence, for the different inputs, there is a different outputs. If the polarities are same polarities, how it is varies. If it is x of t is equal to, here where x of t is equal to plus or -3, where x of t is equal to, okay, 3, and x of t is equal to 3 down at the time. So directly you can estimate that. Hence, for the different inputs, there is a different outputs, of course. So therefore, the system is invertible system. Okay, next, second one. So the expression described the system is, so y of t is equal to 3 plus x of t. That's what the given system is given. So here for x of t is equal to 10. Here try to substitute that, what do you call that, here y of t is equal to 3 plus x of t. That means where 3 plus x of t is given 10. Okay, where y of t is decided. So y of t is equal to 3 plus 10 is equal to 13. Okay, next, and for x of t is equal to -10, the output of the system is, what do you call, so the polarities are changed. That means 3 minus 10. 3 minus 10 is, what do you call, y of t is equal to 3 plus -10 is equal to, what do you call, -7. Solid direct substitution, directly we have to verify that different values using this. So since for the given system, different inputs leads to be different output. Now, therefore, the system is an invertible system. It is proved based on the mathematical examples or real-time example to verify. Next, third, the system is given. The given system is y of t is equal to 5x square of t. Let x of t is equal to 5. The output of the system is, here also direct substitution, y of t is equal to 5. Here same thing, where y of t is equal to 5x square of t, where x of t is given, x of t is equal to 5. The output of the system is y of t is equal to 5 into 5 square. It's also equal to 125. Like this. Let us, x of t is equal to -5. Then the output of the system is y of t is equal to 5 into -5 whole square is equal to 125. Okay, here. So since for the given system, different inputs generate the same output, the system is deciding the factor. We try to decide the factor. The given system, different inputs are generate same output. So therefore, hence the given system is an non-invertible system. So next, coming to this, apart from this, all are what do you call, causal, non-causal, stable, unstable, linear, non-linear systems. We have to classify that this continuous time system and discrete time system. So based on this, the types of the system is involved with CTS and DTS. continuous time system or continuous discrete time system. Yeah. So in general, a system is function or operator that takes an input and produces an output. So a discrete time system has inputs and outputs that are the discrete time functions. That means you usually can estimate that in terms of the CTS and DTS. That means the continuous time signal. In general, system is function or operator that takes an input and produces an output. So that means the system function or operator that takes the input. The input may be either CTS or DTS. A discrete time system has inputs and outputs that are discrete time functions. Okay. So and the continuous time system has inputs and outputs that are continuous time functions. Continuous time functions. Okay, like this, where a discrete time system, where x of n, x of discrete time system, no, that is x of n. If it is continuous time system, here the system is continuous time system. Input is what you call x of n. Output is what you call y of n. Like this. So you can distinguish this continuous time system and discrete time system. The discrete time system is input is x of n. We will export the output is y of n. This is the discrete time signal. Discrete time signal is given to the discrete time system. We will expect that output is discrete time signal. Like this, the input of this continuous time system, input should be a continuous time signal. The continuous time signal is given to that continuous time system. We will expect that output is y of n. That y of n is responsive. The signal is continuous time signal. Okay, like this, right away. This is the most important for this when compared to the previous system. This particular system like continuous time system and discrete time systems. Okay. So like this, you can distinguish the continuous time system versus discrete time system. Yeah, continuous time and discrete time system. Here it is physically a system is a interconnection of the components, devices such as the computer or an aircraft or maybe power plant. Yeah, conceptually, a system can be viewed as a block box which takes an input signal x of t or x of n. Like this, in terms of the block box, it's the importance of the block box. The time they require whatever continuous time and discrete time system. Okay, and as the result generates an output is y of t or y of n. If the result is y of t is the continuous time signal, where the y of n is output, it is nothing but what we call discrete time signal. Shorthand notation where x of tends to y of t. X of n tends to y of n. That means where it is identified that where input is continuous time signal, you will expect that all output is continuous time signal only. Where input is discrete time signal where x of n. Okay. So where x of n, so we will expect that output is y of n. Like this. Okay. This is the variation in terms of this continuous time signal versus discrete time signal. Next, come to the linear system. Linear systems, like basic concepts, we know that a linear system. We will expect that are normally here using this all responses should be linear. Some output response maybe we require non-linear, like this. Okay. So that means here in this case, linear system, the basic concept is, so concepts are other transforms, Laplace transform, Z transforms are involved here. So applications, why they are in the linear system? That applications like instrument response, like right to correct or recorrect or whatever it is. Next application is convolutional mode for seismograms, stochastic ground motion. That time we require linear system. But here in this case, non-linear system. So you'll see that compared to this linear system, non-linear system, linear system is mostly they are independent with or dependent with the Laplace transform or Z transform. Of that we can ready to estimate it is suitable for particular instrument response, maybe for correction purpose, or convolutional model for the particular seismograms and stochastic group motions and so on. Okay, so there is a scope while we are using this all either linear or non-linear. The linear system is very much suitable for this. So understand that many problems in geophysics can be reduced to a linear system, like with help of what you call filter, tomograph, and inverse problems and so on. Okay, so within this, yeah, here definition of the linear time. This all are we know that one. Based on that, to write to somewhat the convolution theorem is involved here. So here two linear system in the successive. This also we have done. Yeah, in various spaces and transforms. If you are using the discrete Fourier transform or Fourier transform versus a discrete Fourier transform, we are talking about continuous time signal, and discrete time signal. If you want to perform that continuous time system as a discrete time system. But here initially that Fourier transform, you have the continuous time to continuous frequency. We require that Fourier transform. If the continuous times to discrete frequency or discrete frequency to the continuous time, we require the bilinear transformation. So sometimes we require from discrete time to continuous frequency, the time we require Z transform. Okay, so like this here, if it is continuous frequency to discrete frequency, the time we require sampling. Okay, so sometimes we require the discrete time to discrete frequency. Discrete time to discrete frequency, we require discrete Fourier transform, DFT. Okay, or sometimes we require discrete frequency to discrete time. The time also we require DFT. Okay, that means we are continuous time to continuous frequency. We require the Fourier transform. Continuous frequency to continuous time. We require the Fourier transform. Yeah, here discrete time to discrete frequency, we need discrete DFT. Discrete frequency to discrete time, we require DFT, discrete Fourier transform. So normally sometimes we require the continuous frequency to discrete frequency, we require to observe. We have to apply this bilinear transform. Okay. Sometimes we require the continuous frequency to discrete frequency, we require sampling frequency or sampling concept. Like this is the importance of various spaces and transforms. This is very much useful for implementing our DSP, digital signal processing. So like sometimes we go the time domain to frequency domain to time domain, or whatever it is, how they are manipulating the signals. We require various spaces and transforms. But here in this case, this is the heart of our Fourier transform as well as DFT, discrete Fourier transform. For distinguish this here, continuous times to discrete time, or maybe continuous times to frequency, continuous frequency to discrete frequency, and so on. Okay, Earth system as a filter. Yeah, normally they are using this Earth system as a filter, like here. So earthquake source where S of t. So now it is affected observing that noise. So basically, including that noise, it is given to that propagation through earth filter P of t. Here also observe that a noise is reflected. Okay, seismometer or recording filter where I of t. Analog, it is given to the analog filter R of t, and it is given to the analog to digital converter. The time by using the sampling, but it is given to the digital signal. The digital signal is processed, the data processing, okay, with deconvolution purpose. The data processing is given to that propagation through earth filter. Again, it is recycling. We have to verify that in between that peak and vertical propagation through earth filter, the decomposition, how it is reflected, how it is affected with the noise. Again, here it is from this the propagation through the earth filter to what you call I of t to R of t is observed, where R of t is ready to measure, calculate S of t, convolve with P of t into I of t. That analog to digital converter, it is given to the digital signal is given to data processing. The data processing, after that deconvolution, okay. So like this is nothing but earth system as a filter. Because of already we have learned that what you call linear, non-linear system, non-linear system, and stable system, and non-stable or unstable system, either causal system or anti-causal system, okay, and so on. So with reference to this, somewhat we require that earth system as a filter. Okay, like this. Right to verify this. Okay, system classification, already we have seen that this all are verified. System representation, maybe gone through this all are. So one thing is linear, non-linear system. After that, systems are classified with the major one. And second, also we have seen that this all are it's around 6-7 systems are required for justifying the what you call linear non-linear system for manipulating the signal. Okay, so like this, a system is set of the linear when it is satisfied the superposition and homogeneity principles consider two systems with x1 of t, x2 of t. So output we will expect this one. Okay, so like this, we have to verify with this how using this all systems, how it is affected with this our signal variation with the help of either using the FF, DFT, or maybe in terms of the Fourier series or Fourier transform of that. It is without this all Fourier series, there is no Fourier transform. From this Fourier transform, to verify that DFT from this continuous times to discrete time, continuous frequency to discrete frequency, and so on. Of that, I will write to verify that FFT, fast Fourier transform in this case. So we require this all system variation or whatever it is. Okay.
Like, share and subscribe. Hit the bell icon for more updates.